One day you will wake up, walk to your window, look up at the sky, and the sun will be everywhere. Not a circle in the distance, the entire sky, red, burning, expanding. And on that day, there will be no one left to scream, no warning, no escape, just silence. Because the same thing that gave this planet its first breath of life will be the thing that takes its last. And the terrifying part? Scientists have already calculated exactly when. This is not a theory. This is a scheduled event, and it has already begun. Here's something that changes how you think about stars forever. The sun is not a fireball. Fire needs oxygen, and space has none. What the sun actually is a nuclear engine so incomprehensibly powerful that it converts 600 million tons of hydrogen into helium every single second. Not burns, converts. Through nuclear fusion, it transforms matter itself into pure energy. And that energy is so explosive that it pushes outward against the sun's own gravity with enough force to keep a star the size of 1 million Earths from collapsing into itself. That balance, gravity crushing inward, fusion pushing outward, is the only reason Earth exists. It's the only reason anything exists in the solar system. And it has held perfectly, without a single interruption, for 4.6 billion years. But it is not infinite. Nothing is. The sun has already burned through roughly half its hydrogen. Think about that for a second. We are not at the beginning of the story. We are at the midpoint. And while 5 billion years sounds like an eternity, the consequences of what's coming don't wait that long, not even close. The first catastrophe arrives in about 1 billion years, and life on Earth, every form of it, will likely be gone long before the sun takes its final bow. Here's why. As the sun fuses hydrogen into helium, the helium builds up in the core like ash in a furnace. That denser core makes the fusion reactions run slightly hotter over time. The result is that the sun brightens, roughly 10% every billion years. That might sound gradual, it might sound manageable, but Earth's climate is extraordinarily sensitive to solar output, and 10% more energy from the sun is not a minor adjustment. It is a death sentence written slowly across geological time. Within a billion years, average temperatures on Earth's surface will climb past the threshold where liquid water becomes unstable. And once that starts, it doesn't stop. It accelerates. Water evaporating from the oceans rises into the atmosphere and acts as a greenhouse gas, trapping more heat, which causes more evaporation, which traps more heat. Scientists call this a runaway greenhouse effect, and it is exactly what happened to Venus. Venus and Earth are nearly identical in size and composition. They formed from the same cosmic material at roughly the same time. The difference is that Venus sits slightly closer to the sun, and somewhere in its ancient past, it crossed that threshold. Today, Venus has a surface temperature of 465 degrees Celsius, hot enough to melt lead, and an atmosphere so thick with carbon dioxide that the pressure at ground level would crush an unprotected human being instantly. That is Earth's future, written in planetary terms, playing out across the next billion years. The oceans go first, not all at once, but steadily. The shallows, the rivers, the lakes, and eventually the deep ocean trenches. As water leaves, the land dries. Forests that took hundreds of millions of years to evolve will wither and vanish. The water cycle that drives weather, erosion, and the chemistry of life itself will grind to a halt. Without liquid water, complex biology cannot function. The last living things on Earth, most likely microbial extremophiles clinging to existence in deep rock or near hydrothermal vents, will eventually find even those final refuges uninhabitable. And then there will be silence. A scorched, airless, waterless rock drifting through space, and the sun won't have even begun its actual death process yet. Fast forward 4 billion more years. The sun's hydrogen core is finally exhausted. Fusion slows, and for the first time in the star's entire existence, gravity starts to win. The core contracts rapidly under its own weight, and as it does, it heats up because compressed gas gets hot. That intensifying heat radiates outward into the shell of hydrogen still surrounding the core, and suddenly that hydrogen ignites. Fusion reignites, not in the core, but in a shell around it, and the energy output is enormous, far larger than anything the sun has produced in its entire stable life. The outer layers of the sun respond to this surge of energy the only way they can. They expand. At first, the expansion is slow. Over tens of millions of years, the sun grows. Then it grows faster. Then it grows at a scale that is genuinely difficult to hold in your mind. The sun swells to 10 times its current diameter, then 50, then over 100 times. Its surface cools as it expands, shifting from bright yellow-white to a deep, smoldering red. This is the red giant phase, and it is one of the most dramatic events in the life cycle of any star. From Earth's perspective, if anything were still there to observe it, the sun would eventually fill a huge portion of the sky. Not a circle in the distance, a wall. A horizon-to-horizon expanse of red. Mercury is consumed first, not impacted, not scorched, consumed, swallowed entirely as the sun's outer atmosphere expands past its orbit. Venus follows, and then the question becomes Earth. Astronomers have debated this. As the sun loses mass during its expansion, its gravitational hold on the solar system weakens and the planets gradually drift outward. Some models suggest Earth drifts just far enough to narrowly avoid being swallowed. Other models show the opposite, that atmospheric drag from the sun's expanding outer envelope actually slows Earth down and pulls it inward to its destruction. Either way, the outcome for anything on Earth is identical. There is no atmosphere, there is no surface liquid of any kind. The rock itself, depending on how close it gets, may partially melt. The concept of Earth as a place is gone. What remains is just a dense lump of minerals and metal orbiting through the outer edges of a dying star's atmosphere. And the sun still isn't finished. After hundreds of millions of years as a red giant, even the shell fusion becomes unsustainable. The reactions weaken and sputter. The remaining outer layers of the sun, the vast, bloated atmosphere it built up during the giant phase, are no longer held in place by radiation pressure. They drift away into space as an expanding cloud of gas and dust called a planetary nebula. It sounds peaceful, and in a way it is. These clouds glow brilliantly as ultraviolet radiation from the dying core ionizes the gas, producing rings and shells of red, blue, and violet light that can span light years. Some of the most beautiful images ever captured by space telescopes are planetary nebulae. What you're actually looking at in those images is a star's death, stretched across space in luminous color. What's left behind when those outer layers disperse is the core, compressed now by gravity into an object roughly the size of Earth but with the mass of a star. This is a white dwarf. It contains no fusion reactions. It produces no new energy. It is simply matter, extraordinarily dense, incredibly hot from residual energy, and slowly, over billions of years, cooling down. A white dwarf will take longer to cool completely than the current age of the universe. In the far, far future, so far it barely has meaning in human terms, it will fade to black. A cold, dark, invisible remnant called a black dwarf, drifting silently through a universe that has long since moved on. So, is there any real chance Earth survives? Physically, possibly. Astronomers discovered a rocky planet orbiting a white dwarf star about 4,000 light-years from here, and that discovery was significant because it suggests some planets do survive their star's death, drifting to wider orbits as the star loses mass. Earth might do the same. It might still be out there, orbiting the cold cinder of our sun billions of years after the last of the sun's light fades. But survival in that context means nothing. No warmth, no chemistry, no movement, just a frozen rock in permanent darkness, caught in the gravity of something that used to be alive. What actually matters, what this whole timeline forces us to confront, is not the death of the Earth. It's the question of what we do with the time we have. And we have an enormous amount of it. The real deadline isn't 5 billion years from now. It's 1 billion, when conditions on Earth begin to deteriorate beyond the point of habitability. That is still a time span so vast that modern humans have existed for less than 1% of 1% of it. But it has a limit, and knowing the limit changes things. Mars becomes genuinely interesting in this context. As the sun slowly brightens and expands, the habitable zone, the band around the sun where liquid water can exist on a planet's surface, moves outward. Mars, which today is cold and thin-aired, slides into the center of that zone. For perhaps 1 billion years, Mars could have stable liquid water on its surface. Whether we could engineer it fast enough, scale it fast enough, survive the transition, those are open questions. But the solar system itself offers us a second stage before we have to think about leaving entirely. And leaving is the long game. Stars smaller and cooler than our sun, orange dwarfs, red dwarfs, burn their fuel so slowly they remain stable for tens of billions of years. Some red dwarfs will still be burning long after the universe is 3 to 4 times its current age. Stars around those stars have a potential window of habitability that makes Earth's billion remaining years look like a Tuesday afternoon. The universe is not running out of time. It is enormous, ancient, and full of slow-burning stars with planets we haven't named yet. Here's what I keep coming back to, though. Every element heavier than hydrogen and helium, every atom of carbon in your body, every atom of oxygen in the air, every atom of iron in your blood, was forged inside a star that died before our sun was born. The sun didn't just give us warmth. It gave us a stable window of time inside a universe that is constantly exploding and cooling and collapsing. We exist in a calm pocket of stellar middle age, around the perfectly ordinary star, on a planet that hit every geological and chemical lottery imaginable. That is not something to take for granted. The sun will die. Earth will either be swallowed or frozen. The solar system will go dark and cold. But between now and then, it's 4.6 billion years of history already written, another billion years of livable time ahead, and the species that managed to go from stone tools to space telescopes in the span of about 12,000 years. If you want to understand just how much stranger it gets beyond our solar system, what waits out there in the deep universe once the sun is gone, the next video is going to take you further than you've probably ever thought about before.